All right, here we go. Unit 2, Day 1, derivatives as limits. As promised, this is very much the first real day of calculus, I would say. This is the first day when you get a taste of what calculus is all about. Turns out that calculus is all about change at an instant. So change at one moment in time versus change over a period of time. And so the first concept we're going to look at here today is the derivative, and we're going to develop the concept of a derivative. We're going to develop the concept of what it is by comparing it to something you might have done in Algebra 2 or in pre-cal or even Algebra 1. So the Algebra 2 level problem in terms of rate of change would be to calculate an average rate of change. You're going to hear me a lot this year. Just pronounce this as AROC just to save time. It's kind of lame, but it saves time. And so say you were asked to calculate the average rate of change between x, which is some time, and x plus h, which is some later time, h seconds later. To calculate the average rate of change, right? Think of it as like distance over time. That's speed. It's your change in y over your change in x, right? This is our slope formula for specifically the slope of the secant line, this red dashed line. Secant, you may remember, is the term for the line that's connecting 2 points on our function. And so if we wanted to find the slope of that line, this is literally just y2 minus y1 over x2 minus x1. I've just labeled it all in terms of x and x plus h. So instead of y2, we have f of x plus h. Instead of y1, we have f of x. But at the end of the day, we're doing really the same thing. We're just calculating what is the change in y over the change in x of this function. That's all average rate of change is. When you see average rate of change for the rest of the year, you want to think, oh, this isn't calculus, this is algebra 2. When we put it in terms of that h value, though, what you can see is that x plus h minus x, that's your x2 minus x1 in terms of x and h, the x's cancel, and you're left with just an h on the bottom, and we're going to see that that's going to be really useful as we transition. Here we go. We're leaving Algebra 2 land and we're going to calculus land. Calculus goes from average rate of change to instant rate of change. And so instead of saying what is the rate of change between these 2 points, I'm asking what is the speed at a single point? What is the instantaneous rate of change? Instant, 1 moment in time. The instant rate of change at a value, not between 2 values, but at one very specific snapshot in time. And so what I really want you to understand here is we need a new tool, because how are you going to calculate the slope with only 1 point? Not 2 points, but 1 point. How are we going to calculate the slope? And when I say calculate the slope, I mean really calculate it. Yes, I get if you draw this, what we call the tangent line, the derivative is the slope of this tangent line. And yes, I get that, like, if you could do it by hand, you could like eyeball and guess, but you wouldn't get an exact answer. You wouldn't be sure. And calculus gives us techniques to find out analytically, meaning not with a graph, with using algebraic techniques to find the slope of that tangent line. And this is how they did it. This is one of like the all-time greatest human achievements, is figuring this problem out. And the way that they did it is to say the following. Let's pretend we start with the problem that we just had before. We're going to find the slope of that tangent line. And as far as approximations go, that's not bad. Those are both positively sloped lines. Maybe the green one is not high enough. It's too low. So what they're going to do is they're going to say, okay, let's bring this back. Instead of this point here, let's bring it in. Let's bring it in and let's bring it closer. And let's find the slope of that line. Now we're closer. Let's bring it again. Let's find the slope of this line. Closer. Let's zoom in so we can get even closer. Maybe we find the slope of the line. Again, my drawings aren't great here, but I'm trying to connect those 2 points. Maybe we zoom in even further, right? You get the idea. What people figured out we could do is that we could find the slope of this line by finding the change in y over the change in x divided by this distance h, right? This is h, this is the change in x. And like our formula above, we found average rate of change here by doing change in y over change in x being h. What we're going to do in calculus is we're going to say find the limit as that h value gets closer and closer and closer and closer, the limit as h approaches 0. And this is what we're going to call the limit definition of a derivative. Basically, it's what is the slope, what is change in y over change in x as change in x heads to 0. Basically, keep finding the slope closer and closer and closer and closer secant lines until you've basically got to the tangent line. Just keep bringing those lines in closer and closer and closer. This is going to be tricky algebraically. You're going to have to suffer through it for a couple days. But once you've done that, there will be tricks to make derivatives easier, but you do need to develop the understanding first. So I'm going to warn you ahead of time, the algebra here gets rough. And so let's see what we mean here. Let's say we had f of x. Now I'm giving you the actual value. Let's say I wanted you to find, first again, I'm going to do algebra 2 first. Find the slope of the secant line between 3 and 7. And I'm giving you the graph for guidance here, but you wouldn't really need the graph. I could ask you to find that slope between 3 and 7. And so what I'm asking you to do is I'm asking you to find f of 7 minus f of 3, that's y2 minus y1, over x2 minus x1 over 7 minus 3. And so all you'd have to do here to finish this out, you'd actually have to find f of 7. So you'd have to do like negative 7 squared plus 14 times 7. Save you some time here. I'm just going to tell you that that's going to be equal to, 49, as you can read off the graph. And then you'd have to have f of 3, that's negative 3 squared plus 14 times 3. Again, I'm going to save myself some time, confirm it from the graph. That's 33. But the idea here is basically you could calculate the slope of the secant line totally without ever looking at this graph, 16 over 4. The slope of the secant line, the average rate of change is 4. And all that is algebra 2. Rise 16, if not algebra 1. Run 4. 16 over 4. Rise over run, speed of 4. Average rate of change of 4. Calculus is saying find the instantaneous rate of change. And so if I zoom out for a second, right, should our instantaneous rate of change be faster or slower than that average rate of change? Should the change at an instant at 3 be faster or slower? And the answer is it should be faster. We have a steeper line. So let's make sure we get faster here when we get the answer. Find the slope of the tangent line, the instantaneous rate of change for x equals 3, for f of x is this same function. And so again, I'm going to do this once out by hand. The rest of the time, I'm just going to have it pre-printed because this can get pretty nasty. So let's say we're going to find the limit as h approaches 0 of f of x plus h minus f of x all over h. This is what we call, that is the limit definition of the derivative. And I'm going to plug in these values. I'll do it in red so you can see what's happening. I'm going to plug in x plus h to my original function. So my original function, I'll do this in parentheses, is negative x squared. I like to just do this by leaving these blank and then filling them in, plus 14x. And I'm actually going to need more space there. And what we're going to do is we're going to fill in x plus h, because that's what f of x plus h means. It means everywhere you see an x, fill in x plus h. Then we have minus f of x. So we're going to have minus a whole nother parenthesis just to make sure we don't mess anything up here. Minus, now this is just f of x. It's negative x squared plus 14x. And all of this is going to be over h. Okay? So, and technically I should be writing this limit statement every time. All I'm doing is rearranging and rewriting this limit statement. So let's multiply this out. This is the same thing as the limit as h approaches 0 of, right, x plus h squared. That's negative. If we binomial multiply, so if we expand this out, right, that's x plus h times x plus h. We'll have x squared we'll have xh times xh, we'll have plus 2xh plus h squared. Woo! Now we're cooking. Plus 14, going to distribute the 14. 14x plus 14h. Stick that all in parenthesis. Now I'm just going to distribute this negative sign. Plus x squared minus 14x. This is the longest one, I promise. All of that over h. Let's distribute that negative sign. Again, just doing it one step at a time here so you can see this all. Limit as h approaches 0. And these you kind of earn your stripes here. You got to do this for a couple days, and then I promise I'll show a better way of doing this. This isn't going to be what calculus is like, but you do need to understand why this works. Plus 14x plus 14h plus x squared minus 14x. All of that. Also, I just want you to see here that I'm suffering with you, so I don't want you to think that I'm not doing it. So now what you're going to see is a lot of this stuff is going to cancel out. It's going to be a bloodbath. Negative x squared plus x squared. We got plus 14x minus 14x. Okay, so here let's see. Now we're looking a lot better. We got the limit as h approaches 0 of negative 2xh minus h squared plus 14h. And you might think, okay, maybe we're ready to try to plug in. If we use direct substitution, we get 0 over 0 because there's an h in every single term. So we're not ready yet. We're going to cancel. We're going to factor out an h. So we can divide all of these terms by h, and we have the limit of as h approaches 0. And all I'm doing here is I'm dividing all of these by h. So the first term becomes negative 2x. The next term becomes minus h. And the last term becomes 14. And so once again, we've factored, we've canceled. Now we're ready to plug in 0. What that leaves us with, and again, we're plugging in for h, not for x. That leaves us with negative 2x. The minus h goes away, plus 14. And by God, that is the derivative of this function. That equation, which we are going to use this new notation, f prime of x, I'll give myself a little bit more room here. The derivative, we're going to call that f prime of x, equals negative 2x plus 14. And what's crazy about that, right? Zoom way out and let's talk about what we've done. We have found, we started with a general equation for slope. That's this. We started with a general equation for the slope of a line, change in y over change in x. We found the limit as the change in x, which we're calling h, approaches 0. We work all that out and we get negative 2x plus 14. That equation will tell you the slope of any tangent line you want, including the one we were asked about, f prime of 3. If we do f prime of 3 here, negative 2 times 3 plus 14. That's negative 6 plus 14. That's 8. The slope of this tangent line is 8. It is up 8 and over 1. If you pick any x value, you can draw a line tangent to that curve, and the derivative will tell you the slope of that tangent line. So our key points here. Number 1, the average rate of change of a function is the slope of the secant line, the line connecting 2 points. That's algebra 2. The instantaneous rate of change is the slope of the tangent line that touches at just 1 point. It just touches barely. That's the instantaneous rate of change, the slope of the tangent line. This is what calculus is all about, key point 3. Calculus is all about change at a moment in time versus 2. Finally, the fourth one, the new most important term for today, the derivative. Literally the entire first semester of a college calculus course is on the derivative. It is the slope of the tangent line. It's the change in y divided by the change in x as the change in x goes to 0. is the single most important sentence in all of AP calculus, in all of calculus. I'm not joking. The derivative is the slope of the tangent line. The number of times that I will say in this class, if someone will ask me a question and I'll say, what is the most important sentence in all of calculus? The answer I'm always looking for is the derivative is the slope of the tangent line. So whenever you hear me say, what is the most important sentence in calculus, the answer I'm looking for is the derivative is the slope of the tangent line. It tells us the instantaneous rate of change. And we're going to work through that. That's going to be what we spend months working on, is applications of the derivative. Trust me, you're not going to have to always do that limit definition. We're going to find tricks to doing that. But that's what we're going to be working on.